in your pupil or not. Great raging debate, fun and games. The other issue to deal with eyepieces that's rather important for us, especially here in Manitoba, is eye relief. This is the distance at which you want to place your eye away from the eyepiece so that you can take in the entire field of view. And eyepieces come in various amounts of eye relief. There is a general formula that you can look at that goes back to that first drawing of an eyepiece. It shows that the ability of an eyepiece to bring everything to a focal point here is pretty much the same as its focal length itself. So a 20 millimeter eyepiece, like a 20 millimeter Losol or an ortho, will usually have about 20 millimeters of eye relief on the other side, which means you can place your eye 20 millimeters away from that eyepiece and still take in the whole field of view. A 10 millimeter eyepiece, you got to get within 10 millimeters. 5 millimeter, and you're scrunching your eyeball right in there. So eye relief is very important to us here, especially if you're going to try to do any observing in the winter time. You have an eyepiece with 5 millimeters of eye relief, and I guarantee you you'll be there for maybe 10 minutes before that thing is frosted and fogged over just by your eyeball. So you might want to choose eyepieces that are going to give you constant, or at least generous, eye relief. And while I gave you this formula that sort of talks about, the shorter the focal length, the shorter the eye relief, we've got ways of cheating that now by using certain eyepiece designs that can give you constant 20 millimeter, say, eye relief. So you might want to look for those. And especially if you're going to wear glasses while you're doing your observing. And like a telescope will correct if you're just near or far-sighted. But if you've got some wonky astigmatism happening in your eyes or whatever, then you're going to want to use your glasses, which means you're really going to want to use eyepieces that are going to allow you to get your glasses jammed up between that eyepiece and your eyeball there so that you can make use of that.
Gary, wearing glasses, would it slow down the seeing up of your eyepiece?
Yes, actually it does. And sometimes I can deliberately put, I don't have any astigmatism, so I usually let the telescope correct for my vision. But in the wintertime, sometimes I'll put the glasses back on, suffer the little bit of field of view that I may not get, just because that barrier in between me and the eyepiece keeps my eyeballs from steaming up that eyepiece. It does work. But it's a bit of a sacrifice. Just be better if you had an eyepiece that had the better eye relief. And here's just sort of a general guide showing you the ways in which people who are going to wear glasses, tell us a British side, that versus what you do with a bare eye, you can get away with eye reliefs that are much less and still take in particular fields of view. Notice, if you want to take in very large fields of view, you're going to need to have more eye relief to do that. And here's the opposite end of what we've just been talking about. This is a case where some eyepieces, and these are the ones with very long focal length, so we're talking the 30, 35, the 40 millimeter eyepieces, your very low powered eyepieces. A lot of them have too much eye relief. In other words, if you tried to scrunch your eye right in, you would just notice this tunnel vision happening. You'd notice that the field of view just sort of disappears into a wobbly little bright patch of light. Because what happens is you're not able to get your eyeball at the exact right place you want it to be to take it all in. And it starts to suffer some nasty vignetting. So especially with the longer focal length eyepieces, you might find that you have to keep your eye a particular distance away just to get the whole field of view in. You can't get too close like with the shorter focal length ones. And then you're going to have a problem of trying to keep your head and your eyeball exactly on the sweet spot there. And that can get tricky when it's far back from the eyepiece. A lot of eyepieces come with little guides to help you locate your head. I noticed with beginners, one of the biggest problems is just holding your head still enough so that it would work out for them. And part of the problem there is, again, the tremendous eye relief of some of the very long focal length eyepieces. You've got to have something that will help you locate your head. A lot of eyepieces now are coming out with these fancy click, 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 cone-shaped guides so that you know where to place your eyeball. You've got some sort of frame of reference of where to put it. Especially trying to find it in the dark, it's kind of a helpful thing. So there's a lot of the new eyepieces coming out that will help you, especially with the low-powered eyepieces, locate your eyeball in the right place. And here's the kind of thing we're talking about. The kidney bean effect is usually referred to talking about a particular kind of eyepiece. It was really made popular, if that would be notorious, I guess would be the better word for it, by the original Nagler series. Wonderful, sharp, wide-field eyepieces, but if you didn't keep your head exactly where it had to be, you would suffer these kind of blackout effects where part of the field of view would just seem to black out on you. Now, certain eyepieces do this more often than others, and just because an eyepiece in the store where you look at suffers kidney bean blackout type effect doesn't necessarily mean it's going to be bad for you under the skies, because part of what's happening here has to do with just how dilated your pupil is. So an eyepiece could be perfectly good in dark conditions when your pupil is very large and be really crappy in daylight circumstances. So don't write off an eyepiece in the daytime just because it has suffering either total vignetting or a kidney bean effect. And here's what happens at the other end. This is the kind of thing that happens when you have too much eye relief and you try to put your eye too close to it. You'll see that sort of tunnel visioning happening, and you've got this fuzzy edge, and then you just end up with a very tiny little viewpoint. So you have to back your eyeball off to take in the whole field of view. And sometimes when you're looking through an eyepiece and everything's still there, you might notice that there is darkening around the edges. Something is vignetting here. Something is not quite right in allowing the whole light path into your eye. Again, this could be an issue of exit pupil stuff, but it could also be something to do with the telescope eyepiece combination too. And there's a lot of wide-field eyepieces, a lot of the new series of wonderful wide-field eyepieces that are coming out that have kind of the reverse of this effect. They've got what they call edge-of-field brightening. EOFB is the way they abbreviate it in all the conversations on it. Where you've got this eyepiece in a certain telescope, and it doesn't work with all of them. You can stick it in there, and all of a sudden the edges are annoyingly bright. So this is something else you want to look for when you're choosing eyepieces for yourself. Now we've got to deal with aberrations, and here's a whole list of all the technical ways in which we're going to talk about aberrations when it comes to talking eyepieces. We're not going to try and learn them or figure them all out or anything today. I just want to run through them to show you the kinds of things we're talking about. Chromatic aberration. Aberrations in color, where objects, instead of being, consistently colored across the face of it, may have a red outer circle and a blue inner circle to it. That's a longitudinal aberration. I'll show you how the telescope is that. And a chromatic aberration of lateral form is actually quite common. You'll see this in lots of different kinds of eyepieces. Here's the longitudinal one, where it's doing the same kind of problem that we've always noticed with certain kinds of achromatic refractor telescopes. It's just not focusing all the colors at the same amount. And lateral color is when the object is off the center of the field of view. It starts to grab color. And sometimes, if you're like me and you're getting fussy about the edge of your field of view, you want things to be sharp, because when I'm observing, I get distracted really easy. So when I'm looking in my eyepiece and if there's something that looks fuzzy at the edge of the field, I want to go look at it and find out. But here's one of the ways in which something can turn out fuzzy instead of clean looking and make you waste your evenings observing, going after things that just aren't really there. It's just due to aberrations. The farther out you get on the eyepiece, the more likely lateral chromatic aberration is kind of the way in which it gets described in the technical manuals talking about the colors. Here's the way it looks when you try to take a picture of something suffering chromatic aberration. You get the little purple edges, the little yellow and green, limey green things to it. It just doesn't look like a clean image. And this is due to chromatic aberration in an eyepiece. But don't write off all your eyepieces because you see some chromatic aberration, because the atmosphere can work like a giant prism itself. So if you're checking out an eyepiece and you're looking at something low on the horizon and it's not very high up, the atmosphere itself will do this to your object. So don't write an eyepiece off for showing this unless you're looking like directly overhead and it's still showing that. Then you've got an issue probably with the eyepiece, as opposed to just what's going to happen when you look at something way off in the distance. If anyone's been checking out Mars lately, it's got a nice chromatic aberration going through it as well because it's sitting so low for most of the evening. One way to check for it is to see if the colors move as you place the object in different places in your field of view. If the atmosphere is doing it, it'll stay like this. If it's your telescope doing it, the colors will move on it. Spherical aberration. I threw in a mirror here just for variety, but this could equally be a lens that gives it to you, and it gives you the problem of not being able to focus all of the light that's coming in to the same point. Spherical aberration is fairly common, and you can see from this little chart, it varies generally in the style of eyepiece you're using. And surprisingly enough, some of the really nice eyepieces that we consider very nice can have large amounts of spherical aberration. So the lesson to take away from this is, yeah, an eyepiece can suffer spherical aberration, but that necessarily isn't going to mean you're going to throw out your negative. Internal reflections in the eyepieces, in the telescopes, can also give you wonky effects. A lot of this can be eliminated with proper modern multi-coatings, but we've still got some issues to deal with. This is not some fancy flying saucer or anything. This is just a reflection of this star that's been captured by the camera here from internal reflections having to do with the eyepiece issues. And again, you can get just haziness around the star, flaring around the star that can be due to an eyepiece that isn't controlling its reflections. And another issue is field curvature. In other words, when an eyepiece is trying to focus the light, it doesn't necessarily focus it as a nice, neat, straight line, but it can actually give it a bit of curve. Now this may or may not be such a bad thing. I noticed with, especially on a lot of Schmidt-Cassegrains, which already introduce field curvature. And by field curvature is everything is sharp, but it's not all in the same plane. So if you want to see the internal part, you focus a little inwards. If you want to see the outside of your field of view sharp, you just have to give it a little touch back on the focuser. So everything is there sharp, but not all in the same plane that the eyepiece would like to see it in. So you've got that kind of issue to deal with. Sometimes it can actually help and counteract what a telescope is doing. But the issue is, yeah, here is sharp stars in the center and fuzzy ones around the outside. But that can be due, like this is the basic sort of issue you'll see with most eyepieces. Relatively good in the center. How far out it goes before it starts to get wonky is always the issue. One of the problems it can suffer is coma, although don't write off an eyepiece for bad coma. That's not a very common problem in an eyepiece, and it's much more common if you're using it in a short focal ratio Newtonian or a mirrored telescope, which can introduce nasty coma on its own. So you don't necessarily write the eyepiece off for this kind of effect. This is the way in which it looks out towards the edge of the field if you look at it. Faster scopes will show more of this aberration. So there's certain scopes that you want to try it out with, like your own scope, to make sure it's going to work right with it. Astigmatism is another problem that you can deal with. This one is kind of easy to diagnose. Just rack it back and forth through focus, and you should see the oblong form go from this to this, back to this, as you rack it back and forth your focus. So then you'll know you're dealing with that kind of thing. This is a problem for eyepieces more than anything else is concerned. And of course you get all these things combined. And then you throw on top of that the fact that most eyepieces don't give you this wonderful rectilinear type view of your object. Orthoscopic eyepieces are sort of named because that's pretty much what they give you. A lot of the wide field eyepieces we look at will give you some of these distortions, especially a barrel distortion like this, which is fine to look at until you start panning across the sky when things get close and far away, close and far away. Some people actually suffer vertigo looking at this kind of image and get dizzy if they do a lot of panning around the sky with an eyepiece that has nasty barrel or pincushion distortion. Doesn't bother me, I like the ride. So if you've got an image, it's going to be distorted around the edge, and it won't really matter what distortion it's suffering, but it's kind of a good way to describe just how far out from the center it gets before things get a little bit soft and mushy, etc. So that's the kind of thing you'll look at when you go to look at an eyepiece to see whether or not you want to deal with it. But you're going to have to sort of ask yourself what you like about that. Like for instance, back in this view, okay, the edge is soft, it's work. Some people don't care. All they wanted to do was look at the object and send it here anyways. If they wanted to see this, they'd recenter it over there. A lot of people aren't bothered by edge distortion. Other people, it drives them nuts. And I'm one of those other people too, because like I said, I get distracted by anything that looks a little fuzzy at the edge of the field, and I go and start looking for it only to find out that this is just a crappy eyepiece I've been spending my night with. So. On that note, I'm going to end part one so that we can have a finally finishing on time and let this meeting start on time. Yeah.
Is it true you've never gotten rid of an eyepiece?
What?
Is it true that you have never personally gotten rid of an eyepiece?
Eyepieces are a funny thing. And for instance, there's certain eyepieces out there that help to correct certain problems. So you need a lot of eyepieces. You can have a situation where, I know some people that will have 3 eyepieces on a certain focal length. One that'll be just for a wide field of views of, let's say, a reflection nebula that's relatively small. They'll have a very small orthoscopic, or small field of view orthoscopic, so that they get a great planetary view with maximized contrast to it. And then you might have an eyepiece that just worked really great in this one other telescope. Certain eyepieces, like the Pretoria eyepiece, was made years ago that actually helped correct coma in fast telescopes. You almost have to inherit one of those eyepieces now. Guys won't part with them. But so just because an eyepiece has a field of curvature to it or has got some issue, try it in your scope, because your scope might have the opposite sign problem to it, and an eyepiece can actually improve the view over what others might do with it. And this leads me to one of the great conversations that we have at Boston Pizza, and that's why does eyepieces, why are they not made specifically for a telescope? I think if you had a set of eyepieces that was designed to take care of the problems of a particular kind of telescope, you'd have a world-beating situation. But somehow we've got this whole tradition where we keep eyepieces separate from telescopes. Yeah, but for certain ones that custom made, and 200,000. There you go. All right. So, yes, actually, and I've been looking at those things. I'm just wondering if those are just somehow some glorified Kellners. They look like they're Kellners with a particular coating on them, restriction, like Kellners are a very old species of eyepiece. Everyone throws them out or throws them at a bird. But the whole deal there is they can be a really great eyepiece in certain circumstances.
Jerry fades away into the back. Well, welcome everybody. I feel like I'm a little bit of a stranger here because I missed the last two meetings. Thank you, Chris, for looking after the formalities while I was running around in various other places. There's too much sky and too little time. Anyway, we have a very nice program tonight. I think a little bit busy. We'll see if we can get through it on time, and I've shortened my talk to help us do that. How many of you are new here? 1, 2, 3. Well, welcome to the Winnipeg Center, the RASC. My name is Jay Anderson, and I'm the president for the next, 9 months or so, which is incidentally something I'd like you to think about a little. And I don't mean re-electing me. I've already had Jerry with the beginner section. Now I'm going to do the announcements. We have Gail talking about the consolation. Did I say that right? I did. Stan's going to give us another adventure with Messier's catalog, which for the new one, that's a catalog of the brightest and easiest to find objects in the sky, the sort of beginner's list of deep sky objects. Jennifer is going to talk about what's new in the science of astronomy. Brian's going to tell us what's coming up in the next month that we might want to look at. We are running out of darkness, but we'll see what we can find. And Mark is going to tell us a little bit about the Sprucewood Star Party that's coming up later on in the fall. And we have our usual break for coffee at the halfway mark, and then I'll be talking about the Hertzsprung-Russell diagram, which is something I touched on several months back, and I realized that it's probably not all that familiar to some of you. So tomorrow is Astronomy Day. I hope you've all heard about that. We've sent out a few memos about it. But we're going to be setting up in chapters over by Polo Park, a place we've set up for the last couple of years. They're quite welcoming to us. And we will probably have just a table set up. Maybe we'll be able to squeeze some solar observing into it, because there are forecast to be some breaks in the cloud. Actually, maybe fairly good in the morning, but in the afternoon, clouds forecast to come in. For that reason, we've sort of put the evening star party that we would typically hold at the Citywine Park on hold, because it doesn't look like it's going to be a very good night for it. So it'll be cold too. So if we can, we'll do the solar telescopes between 9 and 4, so we would certainly like some volunteers. And how many of you can we count on to come out tomorrow and help us out at the table? Can I have a hand a little higher up? Just so we know, okay. I'm going to be there myself too, so we have enough. And certainly if you're in the neighborhood of chapters, come on by and give us a hand. It's usually not a very onerous project. So we have new brochures. I don't see Jennifer here, but she will give her. Is she? Oh, there she is. Okay, we have new brochures which you can have a look at. We'll be passing those out tomorrow. If you have any reasons why you might need them to pass them out to people that you need along the way, certainly make them available. Brendan. Brendan. Not here yet. You'll let me know if you're going to show up tomorrow. And finally, I've got pizza at Boston Pizza tonight, but we got a few other things. Next meeting, June the 10th, is our barbecue at the Glenlee Observatory. Typically show up after work. There's no fixed start time. It's a potluck barbecue, so bring along something for yourself. And usually there's quite a bit of food there. And we'll have some barbecues set up so that Everybody can cook what they want to bring, there's tables there, of course there's a microwave in the warm room, and there's kettles for coffee and tea and things like that. So there won't be a meeting here next month, but we'll send out notices about it to everybody. Usually good fun, and if it stays cold until then, we may even not have any mosquitoes. Had a meeting with Nature Conservancy a couple of weeks back. We've been sort of going back and forth with them about their dark sky site out near Tolstoy, and it turns out to be a little bit of a misunderstanding between us. They thought that they would be doing us a favor, and we thought that we would be doing them a favor. And the upshot of it is that there is a site, 22,000 acres out there of prairie grassland, and if you want to go out there and get a really dark sky site, it can be arranged with the Nature Conservancy people. We're not going to do anything formal out there in the way of a star party or anything like that, because we have other options. It's possible, I suppose, that someday if we get flooded out once more in our first Lindley Observatory when the rain comes up, that we might just move the whole thing out that far, but it is an 80-kilometer strip from the south end of the perimeter. So that's pretty typical of where you have to go these days to get really dark skies. It's not very far from St. Malo, where Kevin and a number of others have done some observing in the past. So they have a house there, and we didn't explore it, but I think the house can be made available to get warm, power can be had, and so on and so forth. So what we need is people who say, yes, I want to use it, and then we'll work our way gradually into the circumstances when we get out there. The National General Assembly is in London on May the 19th starting. We have representatives for the National General Assembly, both of which cannot go, and I am going, so I will act as our rep, which is interesting that we can't persuade people to go to London even when we pay their way. The brochure I've already mentioned. There's a number of magazines to be given out here, and I believe Ian has brought some books to me, or will be bringing some books to give out. We're going to have a draw for those, so we'll be passing out tickets, and we'll do the draw during the break. And Mark, want to come down and say something about Spruce Woods, or do you want to leave it till later? Because I know I have you twice on the schedule here. Okay. So, any questions about the future? Barbecues are pretty easy to take. There's no lectures and no math at the barbecue. Telescopes will be out. If you haven't been to Lindley, it's a good time for you to find out what kind of equipment we've got out there, because it's yours to use. All right, Gail, I guess it's your turn. If I can find my tracker. I thought you were going to speak up to this.
Can you hear me? How do you know what I said?
Yes.
Just south of Sagitza and Delphinus, and south of just north of Sagitza and Delphinus, and south of Cygnus, we see Volcatula, the little fox. Although this is a very small constellation, it is a very interesting one. It was invented in the year 1690, so it's fairly modern as constellations go. It was only made up to fill up an empty part of the sky. This constellation was originally called Vulpecula cum Unser, which is the fox and the goose, but we don't see the goose anymore on the star charts. Foxes have always had a bad reputation as chicken thieves. But really, they're good for farmers because they eat mice and they eat insects that destroy crops. So even though they look a lot like dogs, they really do act more like cats. They hunt at night, they eat mice, and they have long, fluffy tails. When the summer triangle is high in the sky, you can discover the fox by looking about halfway between Vega and Altair. But you'll have to look closely because his brightest star is only 4th magnitude. It's a red giant, and you can see it naked eye only from a very dark location. Vulpecula is 25 degrees from east to west and only 10 degrees north to south. But since the plane of the Milky Way passes through him, there are lots of star fields to look at. If you scan this area with binoculars, you'll see oodles of beautiful star fields and open clusters, and he even has a Messier object. Vulpecula has the finest example of a planetary nebula for small telescopes, M27, the Dumbbell Nebula. I am going to resist the very obvious temptation to associate this with any of our members. I will only tell you that it has this nickname because of its shape, which should be obvious even to all of you dumbbells. You can see M27 as a faint fuzzy with binoculars, and in a telescope it's a really great sight. This is the very first planetary nebula that was ever discovered, and it was by our friend Charles Messier on July 9th, 1764. And that just happens to be my birthday, and I meant the July 9th card. As we're looking at the dumbbell, we happen to see it from its equatorial plane. If we saw it face on, it would very likely look like a ring, like the Ring Nebula, or the Helix, or my personal favorite, the Cat's Eye Nebula. M27 is without doubt the most impressive object of its time in the sky. Its most luminous region covers an area of 6 arc minutes with a faint halo that extends to more than 15 arc minutes. That's half the size of the full moon. You can easily find it with binoculars or a small telescope. I use the stars as signals, and I imagine that I'm completing the rectangle, and there it is. In binoculars, it's a great puff of light and a very pretty field. This is one of the brightest planetaries at magnitude 7.4. The huge cloud is a shell of gas that was expelled from a dying star. The star first ballooned into a red giant, which is a cool star hundreds of times its previous size. Then the star kicked its outer layers out into space. What remains of the star is extremely hot, so it produces a lot of energy, making the expanding shell of gas glow like a neon sign. The brightest part of the nebula is expanding at a rate of 6.8 arc seconds per century, which makes it appear to be from 3,000 to 4,000 years old. The central star of M27 is magnitude 13.5, and it's an extremely hot blue dwarf with a temperature of 85,000 degrees Kelvin. This is one of the most observed objects in the sky, and it should be. It's great. Here's a cute little cluster of stars called the Coathanger cluster. It's probably really an asterism. It's not a true cluster, it's just a chance alignment of stars that are at different distances. It was discovered and described by the Persian astronomer Al-Sufi in the year 964 AD. But I doubt that they had coathangers in those days, so I don't know what he called it then. Charles Messier must have seen it, and so did the Persians, but it has no Messier or NGC number assigned to it. The whole cluster is called Grouchy's cluster, after the American astronomer who drew a map of it in the 1920s. It has about 40 stars in a 1-degree field, which is the size of the full moon. The Coathanger inside of it is 10 stars ranging from 5th to 7th magnitude. It's a straight line with 6 stars, and then 4 stars making the hook. See the Coathanger? Grouchy's cluster can be seen with the naked eye as an unresolved patch of light, but you'll need binoculars or a low-power telescope to see the Coathanger shape. You can find it very easily by sweeping a line from Altair to Vega, and about 1/3 of the way up, that's where you'll see the Coathanger against the darker region of the Milky Way. The Milky Way is passing right through Vulpecula, so our little fox is just full of open clusters. NGC 6940 is very bright, it's magnitude 6.3, and it's very large, 31 arc minutes in diameter, as big as the moon. It's very rich, it has 100 stars, magnitude 9 and fainter. It's a very condensed open cluster. It's 3.5 degrees southwest of 51 Cygni, which is that bright star in the Veil Nebula. There's an 8th magnitude orange star in the field. The cluster is particularly impressive because it's positioned in front of dark nebula in the Milky Way. The stars form a semicircle. Like that. This is a very nice one. Open cluster 6802 sits on the eastern side of the coat-hanger cluster. Its magnitude is 8.8 and it has 50 stars magnitude 13 and fainter. It measures 3.2 arc minutes across, so you'll need at least an 8-inch telescope to appreciate this one. And anything smaller, it would just be a hazy bar. NGC 6820 is a small reddish diffuse nebula, about 5.5 degrees southeast of Alberio and 4 degrees east of the Dumbbell Nebula. It has a round shape with a diameter of 40 arc minutes, and there's a small oval cluster inside of it, which is NGC 6823. Because Vulpecula is not an ancient constellation, it doesn't have any stories associated with it. But there is the Aesop's fable of the fox and the cat. A fox was boasting to a cat about its cleverness for escaping its enemies. I have a whole bag of tricks, he said, which contain 100 ways of escaping enemies. I have only one, said the cat, but I can generally manage with that. Just at that moment, they heard the cry of a pack of hounds coming towards them, and the cat immediately scampered up the tree and hid herself in the branches. This is my plan, said the cat. What are you going to do? Fox thought first of one way, then another way, and he considered another one, and while he was debating, the hounds came and captured him. Now, that's not a very nice happy ending for the fox, but the moral of this story is that we're not supposed to think, we're just supposed to act. I don't think I like that moral either. I have been told I'm not putting enough cat pictures in my constellations. So I'm going to mention another very famous fox in literature, and I know you've all heard of him. He's in the story of Pinocchio. And it just so happens that this fox's best friend was a cat. The end.
We'll have to persuade Gail to get a dog. Okay. Stanley, I know you're loaded up in here somewhere.
Took a lovely picture and sent it up on the wire this past week, and I thought I'd put it up there because it's sort of indicative of how things are going these days. But probably the object that you're going to be seeing most of is the sun, because the days are so long. That's a nice shot. You can see the planet tree over there. That's one of the problems about this time of the year, is that there's a limited amount of time to do observing. So I'm going to try to tell you about some objects to look for, but you can't spend a lot of time looking for things. I just wanted to go a little bit over some of the stuff that's in the observer's handbook. When you're trying to figure out your observing time and when you're going to be looking at things, you can go to the observer's handbook and it'll tell you, this is the numbers for the date of May 14th, it'll tell you that the sunrise is at 04:15, sunset is at 19:38. The thing is, then you have to take into account the daylight savings time equation, so you add another hour to that. And then you have to consider that within the time zone, Winnipeg's located about the middle of it. So they're not right at the edge where it would be 0, or at the far edge where it would be 59 minutes. They're about the middle, which is about 29 minutes. So you add the 29 minutes to it, there you go, the 5:44 in the morning, the sun rises, at 21:07 or 9:07 in the evening, the sun is setting. Well, that doesn't help us because we don't start observing once the sun sets. You have to wait until the sky darkens. You have this thing called twilight. And there's the definition of it. It's the interval when the sun, or the light from the sun, the sky glow interferes with things that we see. Now there's three types of twilight. three varieties of twilight that are talked about. Civic twilight, that's, the sun gets a little bit low and all the streetlights come on. So when that time frame, that's when, you could just start to see some planets and some things. Then there's a nautical twilight, which is when it gets a little bit darker, but that one really doesn't apply to us at all either, because during nautical twilight, you'll start saying, I still can't see all the stars the way I'd like to. So in fact, for you to truly see the darkness of the evening sky, you have to wait till the sun is the center of the sun is 18 degrees below the horizon. And that's when the sun does not contribute at all to the sky glow. Well, this time of year, just the whole mechanics of it all, that takes a lot of time. So when you go into the observer's handbook, once again, you take a look at your twilight. There's some times for it. For the morning it says 01:51, and for the evening it's 22:05. Well, what you do to get the correctness for how it applies to us is, once again, you have to add that 1 hour for daylight savings time correction, and then you have to add the 29 minutes. So there it is, another hour and a half added to the 1:51. 3:20 in the morning is when the twilight begins, or the end of the night, and we start to see the end of Australian twilight. And 11:34 p.m. is when the evening twilight has ended. When you take a look at that, that's 2.5 hours after sunset. So it really tells you that we lose a lot of time of observing here in the province, being so far north. So basically, when you do your observing, one thing is to consider is always to try to be observing where you're looking away from either the western horizon in the evening or the eastern horizon in the morning. Now, when it comes to selecting some objects this month, I'm assuming that all of you did a lot of observing in the last couple of months, with all those objects high in the sky, seeing all the galaxies out there in Virgo and Coma. Right? So we're going to be looking to an area where there's not a lot of objects, unfortunately. And basically, at about 11 o'clock, what I'm suggesting you should start trying to do some observing, up to 11:30, a little earlier, 11 o'clock, of these four objects at the top are just west of meridian, so they're just past part of the highest of the sky. And they're lower. These four objects have to be lower to the south. So these are four objects that are a little bit more challenging. Two will be relatively easy to find, but are quite nice ones, and two are a little bit more difficult. So checking out the handy planisphere, you'll notice over here, it's about 11 o'clock, somewhere in the time frame. This is just before 11. So we'll have the date and the time, and it's the shortness of the sky. This is sort of the area that I'm talking about. We're specifically surrounding Corvus. Two things I want to remind you about when I'm talking about this is I'm going to be talking about using the finder scope to find the objects and then aligning it for your scope itself. And I want to remind you that the talk I gave a couple months ago, when you use finder scopes, depending upon whether it has a 45 or 90 degree wrinkle here, and then at the side, or whether it's straight through, it still sort of flips things relative to the way you see a chart. You look at a chart and you see the stars in a certain way, but when you look through a telescope or fractal telescope, things get switched around. So keep that in mind when you're looking through your scope and how to find the object. And they said, and the part and parcel that I was talking about is that definitely you have to know which way is up, which way is down, which way your scope is moving, relative when you're looking through your finder scope. I also talked a little bit about the geometric method in the past. So it's the ability to find objects by sort of lining them up off of other objects and such. Using this as a triangle in order to sort of center your finder scope in that area to find those objects. Just a little review in case you weren't listening to me at other meetings. So I'm going to be talking about a few objects, and the first one I'm going to start talking about is M104. M104 is a very nice object. This is the 7 degree field of your finder scope. So actually, when you find Corvus, which is not Hercules. Somebody I knew used to think, hey, that's like Hercules, but when you find Corvus, you use the star here at the top to basically put it right at the bottom of your microscope and search in this area off the and run forwardly, just off the side, so it's within the 7-degree field. The Suburban Nebula is actually not in Corvus, it's in Virgo, but it looks like it should be in Corvus. It's a fantastic galaxy, beautiful galaxy, 8 magnitude, fairly large, 7.1 by 4.4, so it's a decent size. It's not too small. You have to always consider the size of the object that you're looking at. That's about a quarter of the size of the full moon. It is visible, bright enough to be visible with binoculars. But all you see is basically a little fuzz in the binoculars. You'll be able to tell there's something there, but it's not a star. In a smaller scope, like a 6-inch scope, you'll just barely be able to see that there's a little bit of a dark light. Now this is a drawing, a sketch of the object. And I use sketches because these more represent what you see with your eye as opposed to what you see if I showed you a photograph. Photographs and sketches are very different. Sketches tell you what the person is actually seeing. So this is an approximation with an 8-inch upswing of what you'd see. It's actually quite popular, or quite attractive object in an 8 to 10-inch telescope, and that's like the ones that you lend out. So here's a field view with an 8-inch scope, fairly large size. I think this is about 100 hours this particular object is being shown. When you do messy objects, if you have the opportunity to look at it with a larger scope, I'd suggest, because this actually is quite a magnificent object in a 16 to 18-inch telescope. So for people like Terry, who brings over his large telescope to the SWSP, this is the kind of object that we line up and take a look at. The next object we're going to be talking about is a little larger cluster, the M68. And again, here it's easy to find it. If you put data in the field of view and line up your microscope like that, it should be fairly easy to spot and then center on the object. It's a little bit fainter. In fact, this kind of sketch shows it. It looks a little bit faint. 12 arc minutes, so it's fairly sizable. It's not quite half the size of the moon. In binoculars, it will just show up as a small truly kind of object that an essay would look at and think, I wonder if that's a comet. No, it's not. So it stays in the same spot all the time. A small scope will show it as a little ball of light with a little bit of graininess to it. An 8 to 10-inch scope will resolve it as a very bright little cluster with a bright little core to it, and just be able to pick up stars on the outside. And then the larger scope, like the 12 to 14-inch scope, will start to resolve more or less the stars on the outside, and the inside will be a little smaller, but the outside will start to show you individual stars. The next object, thinking just a little bit off of Corvus, just off of here in Hydra. And again, you will set up your finder scope like this, off of gamma, and then you'll see that there's a little arrowhead, a colorful arrowhead. There's 3 stars that sort of form like a little arrowhead, sort of pointing towards, looking away from M83 towards gamma. So you set the scope like this, and then you set it up with a quick arrow, and then you should be able to see M83. It's a barred spiral galaxy in Hydra. It's going to be fairly low on the horizon. This is one of those objects that I was kind of looking. It's the only time for us to be looking at this time of year. It's still going to be low. It's going to be a little bit more challenging, although it's bright. It's 7.6, and we can be seeing the binoculars. It's challenging because it's lower in the sky. 13 by 15 arc minutes, so fairly large. With an 8-inch telescope, with the lender scopes again, have a nice little dark. You should be able to see that little dark across it, and just barely start to see the arms on this like that. In a 12 to 14-inch scope, again, you want to look at this with a larger one. You'll see that the arms are actually 1 inch shorter like that, and the other one is longer. It's actually almost wrapped around and turn around the other side of it. This always tells you that your message, you always try to see with the largest scope possible. The fourth object, which just happens to be in the area, it's just a little bit further off of the area we're looking at Hydra, which is just off of this area. But this one's a little bit easier to see, just for Ophiuchus. This little flattened diamond stars is actually visible to the naked eye in dark skies. So we see surface here. You can put down these three stars and then kind of look at this little pattern of the stars and center around 5.5. M5 is actually quite bright. It's a globular cluster. Magnitude 5.7. Unless your eyes are very good, I question whether you'd be able to see naked eyes, but we might be able to see the very vision. 17.4 Arcturus, so it's a pretty sizable object. In binoculars, it'll be a nearest draw with a cluster. Circular, you'll be able to see truly detect the second difference. Very, very, very core. A 4-inch will reveal it like a ball of cotton and start to resolve stars on the outside. 8 to 10 scope will show it's actually a pure splendid globular cluster. Again, irregular. The core isn't quite circular, so you'll be able to pick that much straight to that, and you'll be able to start shooting the stars moving the outside. And it is actually quite spectacular object to fall with your scope. It is one of the finest globular clusters there in the sky with M13 as well. So those are the 4 objects for you to go hunting for this next month. You're going to need your SA certificate. You pretty well got to do it all, so now's the time to catch the 4 of them. And I'm going to just tell you that those charts that you saw, or some of the charts that you saw there, I actually picked up from this one. It's called Star Watch. And I picked this up actually at the Children's Hospital book fair. But every now and then you come across something like this. It's actually a very nice book. It's like with all the objects. So if anybody wants to see this, and we're hunting for it, let me know. Thank you.
My name is Brian. I'll do what's up for the next couple of months. I'm going to start off with the planets first. So in the month of May, we have Mercury, that's going to be well facing in the morning. Venus is too close. It's not to be observed. My favorite is Mars. I love Mars. So it's going to be the closest point to Earth on May the 3rd of this month. Jupiter is still well facing the sky, and Saturn is still retrograding in Ophiuchus? Constellation Ophiuchus. Is that right? Ophiuchus. Ophiuchus, thank you. All right. I know it's only for this month. I'm going to stretch it a little bit more to for June. Again, Mercury's still in the morning sky. Venus is still too close. Jupiter is going to start to set after midnight, and of course Saturn is still visible. But what's nice about Mars is it's going to be stationary. It's going to appear stationary around on June the 8th, I believe. Next we have, now for the month of July, again, we'll stretch it out a little bit more. Mercury's going to be in twilight. Now Venus is going to be popping up again around the sun, once it comes around the sun. And of course we have Mars. It's going to be up pretty much all night. And unfortunately, Jupiter is going to be a little lower in the evening of July. And of course, Saturn still placed in the sky in Ophiuchus constellation. Now, my favorite is Mars. I really like Mars. big way. And I'm happy that this year, when I first started off here, it was like, I think, 2012, so the size of Mars, like, was 13 marks. This is how Mars orbits the planet or the sun, reference to Earth. So blue's going to be Earth, red's going to be Mars. So we're at 2016. So it reached its opposition on May the 22nd. So on 2016, so it's going to be 18 marks across. And well, in a couple of years, we're going to have it where it's going to be 24 marks across. And I love this scale here because you can see how big it is compared to other years, especially 2003, you're looking at 25 marks, and then 2018, so that's a huge difference between the years. Now, hopefully this works. Okay, I got this here. Okay, so unfortunately Mars is not going to be high. It's going to go 18 degrees above the horizon. So this is what, yeah, that's its closest point right now, May the 30th, so it's only going to be about 18 degrees below the horizon, which is not too good. Around 12 midnight. And I was going to show you a little bit more, closest to Earth, this one, hopefully it works. I'm going to try it. There we go, it starts playing. So when these planets start to glow, that means they can be observed from Earth. Now this is for 2016, so right now we're in February. So Jupiter, you see from Earth. And which one I want to show this because then we have Mars right here. We're catching up to Mars. Now Saturn's in view. Now it's going to be tricky because right now Mercury's coming up, so we have the transit of Mercury right about now, and then Mars is in view too. And this is roughly where it's made right now. Now Mercury's out of sight. Venus is coming around in view soon. We're still in view from Saturn, still observe Saturn and Mars. I'm not going to play the whole year actually. Give me a while, but what I'm going to do is, let me just if I can replay it for you guys. There, let's play it one more time. Alright, so remember Mars, we're faster than Mars, so it takes every 2 years to catch up to, or we catch up to Mars every 2 years. Again, you see Jupiter, now we're coming up to Saturn, the observed from Earth. Again, we have Mercury, transit of Mercury coming up real soon. So it's May the 9th, so right about now. Alright, moving along. We're going to the next slide here. Alright, so I guess we're not going to have our member sites more later, because, okay, so we need to have pops up on the screen, so around 10 o'clock at night we have Jupiter and the Moon for the public to observe that's going to be canceled tomorrow. Okay, so a little later on, roughly was at 2 a.m. on Saturday, it's showing a little bit what's up. Of course, we have Mars, there's Mars, there's Saturn. Some of the constellations we have up there, of course, is Hercules, Lyra, Pegasus, throughout the galaxy, and Lyra's right here, M57, one of my favorites. And that will be Saturday around 2 o'clock in the morning. Next, for the celestial calendar, for the next couple of months, really, of course, we have the Aquarian meteor shower that peaks on May the 5th, transit of Mercury on May the 9th, Mars, which is closest point to Earth on May the 30th, solstice, where the sun reaches the highest point, which is June the 20th, June the 30th, we have Mars, which is going to be stationary. And then we have the Perseverance that's going to peak on August the 12th. Well, someone says it's going to be rated 110 hours, maybe just down that. And then we have the zodiacal lights starting on August the 3rd for the next 2 weeks. But don't worry, I think the end of September, we have another chance for about 2 weeks near the end. But this time, it's going to be in the morning, just before the twilight. The pretty myriad shower. I wanted to bring this up again because, again, apparently it's from April 19th to the 28th. So there's still a good chance of seeing it. The best time is, of course, going to be near dawn. And, of course, it's created by the degree of comet daily. This is the last part. Comet chasing. I think Jennifer mentioned about this comet here. I don't think you have any really good chance, but it's just the best comet if you want to have a look at it. Again, in the constellation Ophiuchus, they said the core is roughly 7.8, but right with the Stellarium, we're looking at about 13 magnitude. So, if you want to take a photograph, that would be great, but usually it's not going to be impressive. All right, so that will conclude my presentation on what's up. Thank you.
We have some nice views of Saturn by the time we get around to the Sprucewood Star Party. So, Mark, are you going to come down and tell us a little bit about the Sprucewood Star Party?
Okay, this is an update for the Sprucewood Star Party coming up on September 2nd to the 5th. It's a long weekend, so no plans. Well, there you have something to look forward to. And just want to mostly show new members who haven't been with the Star Party what to expect. So these are the reasons why you should come to the Star Party. We've got 3 great nights of observing. Last year we had all 3 nights were clear, so we had a great time. 2 years ago I think we got 2 out of 3 nights, so we always have something to look at, great nights. There's no park pass required this year because it's on a long weekend, and Multiple Parks is giving free admission to the parks. You get a chance to meet RASC members. I know you can talk to each other here, but at the Star Party you can see yourself, doing the things that you want to do. We have a couple of talks, sky tour, binocular tour, equipment tour, so we go around in the field and we look at other people's equipment, give you ideas, if you want to purchase something or what's the best fit for you. You can ask questions if you have questions about astronomy, whether it's observing or what kind of equipment you should buy. You can ask members, any kind of questions you have, and they can give you some answers. And you have swap tables, so if you have some eyepieces or tripod or anything that you want to get rid of, you can just bring it and sell it or exchange it for other things that other members can bring. And to close the Star Party, we have a banquet that's on, I think, Sunday night. And for the questions, these are my questions. It's really been bothering me, and I hope you guys can help me with this. For example, when's the best time to view Venus? Or what's the next great astronomical event in North America? Or who discovered the pulsars? Sheldon Cooper? No, I don't think so, unless they're Big Bang Theory fans. So this is our observing field. It's wide open. We have a few trees, but it really doesn't bother for observing unless you're looking for something about 5 degrees up. I got plenty of room for tents and campers. And at night, our observing field turns magically with a dark sky. I think this is the binocular tour last year. This is part of the binocular tour, or one of our members is a Jedi. This year, we decided not to have laser pointers, only at the sky tour. For many reasons, you know, if people are doing astrophotography, well, we could probably interfere. This was, I think, 4 years ago. Sheila got this wonderful picture of a fireball. It was absolutely amazing. I don't know what magnitude it was. From my perspective, it was like a full moon, so it might have been about magnitude -12, -13. And if you want to see a fireball like this, I think we're due for one. I think we're going to have one this year. Well, one thing, get all your equipment ready before it gets dark. Don't go put your head inside your car to get an eyepiece. You're going to miss it. And especially, don't go to bed. And as I mentioned, sometimes we'll have a cloudy night. When we do, we just sit around campfire and eat munchies or just sing along. Some people bring some musical instruments and we just have a great time. Sometimes the clouds will open up like it did here. I don't know, you just run and get your equipment ready and start observing. Sometimes those holes just close up and then you end up with cloudy skies again. But yeah, so we have a fire going and we have a great time. But nighttime is not the only time that we have something going on. Here is our equipment tour that we have, I think, on Saturday afternoon. Just go around, see some volunteers who want to show off their equipment, you know, whether telescopes or astrophotography equipment. And this is where you can ask questions and get to know what kind of stuff you might be interested in. We also do some solar observing. Got great prominences and sunspots to look at. Or you can challenge yourself and try to look at Venus and Jupiter. Last year I found Venus and it was a really nice crescent. We then have talks at the Interpretive Center in the park. And of course, to cap off the weekend, we have a nice banquet at the Glen Road Community Center. And before leaving, we try to get all together and get a group photo. Shows you how many people come to the start party. We have, what, 50, 60 people, something like that. So information, you can find some in the last two in the Centric newsletter. We'll have more in the next issue or two. The last email list, that's there's some information. We'll send you some information as we have some. But all the information is on our website. Here's a link directly to the event webpage. And we're going to add some more stuff like the schedule and the registration info, which is almost done, so take a look. If you have any questions, well, some of us are here. Sylvia's here, I think. Cliff, are you here? No. Gail and myself. And that's it. Thank you.
All right. Thank you, Mark. We are ready for coffee and whatever other surprise Mark has for us today. So please come down and everybody got a draw ticket.
My last haircut.
I'm going to hold you up and Jennifer's going to pick the ticket. While I'm at it, we have 2 telescopes available for for loan right now. 8-inch loan. Is that what you have, Stan? You have an 8-inch as well? Two 8-inch. 8 inches. If you would like to take one home to use tonight, please talk to Stanley. We would love to get them out of our automobile. And the details on the loan is up there on the board. Okay. Stars and Galaxies. Beginner's edition.
489-448.
489-448. Who's the lucky man? Wait a minute. When you understand that book, you can be president. The universe at a glance.
489-428.
428.
Hey, that's me! Oh, Jerry, one something! Oh!
Yeah, there goes the universe.
The soul story.
I think that's a Yell ticket.
The essential cosmic perspective. Go ahead.
489-437.
437. Oh, here we go. And fundamentals of cosmic perspective. Does that go with the other one?
489-425.
425. Here, over here. And I see we still have some magazines left down here. Help yourself. Okay. Several months ago, I gave a talk about globular clusters, and in that talk, I pulled up from Russell's diagram to talk about the evolution of the clusters, and I realized that I probably should have talked about the Hertzsprung-Russell diagram before I talked about globular clusters. We're going to do it in reverse. So now I'm going to try and cover off the essential parts of the HR diagram. Now, I titled this our favorite chart, but it's actually one of the most powerful graphs or depictions or displays of stars and how stars behave and how stars fit with each other and within, to some extent, the whole of the universe. And it was a major discovery just over a century ago that these sorts of details started to be put together. And the beauty about the HR diagram is that it's really quite a simple thing. It's simply a graph of the brightness or luminosity against the temperature. And we have lots of ways of measuring luminosity, and we have lots of ways of measuring temperature. And so the graph itself can actually have different axes on the horizontal and the vertical side, but they all amount to the same thing and they all give you a similar looking graph. One of the great powers about it is that you can relate where a star is on that graph to all of these other things that I show here. Where it is, how old the star is, where it is in its evolution. You know, is it a young star, an old star? Is it a nearly done star? Is it dying away star? You could talk about its metallicity, which is the elements other than hydrogen and helium that are inside the star. How long has it been around? That dictates how much of the other elements have been created in the center of the star. You can use it to find how far groups of stars are, or even individual stars are. You can talk about what kind of energies where they're getting their energy in their internals, whether or not they're stable or not, whether they're likely to be variable stars or pulsating stars. And all of this falls out of the Hertzsprung-Russell diagram. And so what I'm going to do is go through not only what the diagram is, but trace the evolution of a number of stars through this diagram so that you can see how it works out. When we measure the color of a star, we're actually measuring its temperature. Stars are white hot, they're red hot, they're yellow hot, they're blue hot. A direct relationship between the color of a star and its temperature. And temperature tells us something, if you know the size of the star, how much energy is coming out of it. We're not really concerned too much about the size. All we want to know is how bright is it. We can put a filter on a telescope and we can measure how bright it is in red light. We're going to put a different filter on a blue one, and how bright is it in blue light. And right away we have two measurements that tell us something about its temperature. There are a number of ways to take those colors, and typically astronomers would take 5 different colors. Ultraviolet, blue, visible light, which is kind of an orangey green color, infrared light, and red light. So you don't need all of those measurements, you just need 2 of them. And we have this thing that we call a color index. And the color index is simply the difference between the magnitude in blue minus the magnitude in the visible wavelength. These are not very narrow band filters, they cover a fairly wide range in the spectrum, but they're certainly concentrated in the visible and in the blue end of the spectrum. So you take 2 photographs of the stars, a group of stars, one in each color. You determine the magnitude or brightness that they are, and then you just simply subtract the visible magnitude from the blue magnitude. And if you get values that are below 0, you're talking about a hot blue star, a lot of blue in that signal. And remember, magnitudes work in the reverse. So a negative magnitude is actually a brighter object. If you get Betelgeuse, for instance, which is one of the reddest stars, you can see that its value is 1.85. So you can do it for huge areas of the sky by just taking a big wide-angle view on an ordinary camera, snap your picture through the appropriate filter, and then go through whatever piece of software you want to tell you what the actual magnitude is in these 2 bands. Brightness is a little bit of a different problem because we have 2 things that work with brightness. First of all, it depends on the distance of the star from us and what its intrinsic luminosity is. So a star which is big and really bright, an O-type star, for instance, we'll cover that in a minute, then that may not be very bright to you if it's a very long way away. So you need some way of compensating for the distance. And we do that by calculating what we call the absolute magnitude, which is defined as how bright would that star be if it's at 32.6 light years away from us, which is a distance called 10 parsecs. Parsecs are a fairly specialized unit that's used, you'll see quite often in the measurement of distances of stars, and it's based on how much of an angle they change through, they move through as the Earth moves from one side of its orbit to the other. We're not going to worry about that so much. If you were to put all of these stars, go back. If you put all these stars at the distance of 32.6 light years, you would get a new value. So our sun, which is of course monstrously bright in our own sky at minus 26 magnitude, moved out 33 light years, it's only going to be magnitude 4.8, barely visible to the eye. You take a star like Rigel, which is one of the brighter stars in the sky, it appears to be very close to zero magnitude, but when you move that to 32.6 light years away, its magnitude becomes minus 8.1. And that's because it's at 1,400 light years, so you're effectively moving it much, much closer to it than it's going to get very bright. So you can take a look at these two distances and say that almost 13 magnitudes brighter than our sun. So Rigel is a very, very intrinsically bright star. And similarly, there's other numbers here for Sirius, which is the brightest star in the sky, would actually lose a lot of its brightness if it was moved from 8.6 light years to 32.6 light years. Now, we don't have to use absolute magnitude. We can also say, well, it's 15 times brighter than our sun, it's 1 time brighter than our sun, meaning the same, or it's 0.8 times the luminosity of our sun. So just a different way of measuring brightness on these charts. So what I did is I took the brightest stars from the Observer's Handbook, and these are about 315 of the brightest stars in the sky, and I plotted them on this. And I used the color index, the difference between the two magnitudes here and the absolute magnitude here. Now right away you sort of see there are patterns in this diagram, but they're not obvious. They're not anything what we call rational. There's certainly a collection of stars through here. There's a collection of stars here and here. There's a lot of stars that are scattered around, and I put in a couple of the better known bright stars, except Polaris, the North Star, just to show where they would be. Interestingly, our sun appears pretty close to the bottom of this, and that's because the brightest stars in the Observer's Handbook are really a very poor subset of stars that are visible across the entire sky to much deeper magnitude. It's simply because kind of a very strong selection effect there. I talked about how you could change for different measurements of brightness. So here's where you can plot luminosity in terms of the sun or absolute magnitude here. You can plot the color index, this blue line is visible, but you can also use what's called an effective temperature, which is a measurement of the actual temperature on the surface of the star. Or you could use the color or the spectral class. Now, we've talked a number of times about spectral classes. And stars are ranked from hottest blue stars to the cool red stars through that OBAFGKM classification. Originally, when this classification was started, it was A, B, C, D, E, F, G, but as they began to understand stars better, they reorganized them from hottest to coldest. There's a long-term phrase that we use to remember that, oh, be a fine girl, kiss me. It's a little bit out of tune with current events, so the best alternative I've come across is only boys accepting feminism get kissed meaningfully. If you go out and look, you'll find hundreds of different methods of remembering that phrase. Now, up here, I've sort of schematically placed the 315 bright stars. So right away, we see these stars over here tend to be the brighter stars. Now this is not an exact placement, this is pretty much approximate. Because the sun is in about here and should come over, so it could probably be slid over a little bit. But from this we see that we have some cool stars on this side. They come in temperatures from 2,500 up to say 5,000 degrees. Over here we have some very hot stars at 20 to 25,000. But right away we see that by interpreting what we mean by color index, we are also finding an awful lot about something about how the stars are sorted from one place to another. As I said, this thing started about a century ago, and it started when the actual background measurements became possible, when we started to see some idea of distances and temperatures, or some kind of a substitute for temperatures. Star distances were not well known in 1911, but some of them were able to be determined by the shift in the sky they make as the Earth goes around its orbit. They sort of make a small movement back and forth. But the way they really got around it is you could plot all of these stars without knowing their absolute magnitude if you know the stars are all at the same distance from you. And the way to do that is you go look at clusters of stars. Because just sort of by definition, clusters of stars are all together in one place, and so you don't have to compensate for the correction in their brightness because of their varying distances. It means you can't compare one cluster with another cluster, which is at a different distance, but you can compare all of the clusters in one star with each other. And so, Hans Rosenberg was the first one to sort of make these graphs, and he used the stars in the Pleiades cluster, which is certainly a very bright one, and kind of came up with a graph that was like the ones I just showed you. You know, something is happening in this graph, but I don't know what it is. But stars seem to want to collect over here, or over here, or over here. And very shortly afterwards, Hertzsprung in 1911 used spectral type for temperature, and that means an OBA-FG category. So those were easy to determine by looking at the spectrum of the stars. So we put the same cluster, the Pleiades. He also included the Hyades, which is another cluster. But now he had to have some kind of a distance, at least know a rough distance to the Pleiades and the Hyades to be able to recalculate the brightness in here in order to put them together. But he wasn't quite ready to do that, as you'll see in the diagram or two, so he kept them separate at the first, and noticed that they did form the same kind of a pattern. Russell came along a little later. He was starting to use stars that had known distances, and he added them into the Hyades cluster. So he was probably the first one who was able to put those two together, combining stars from different clusters in different regions of the sky instead of using all one. And here the two honorable gentlemen are looking. Well, one looks kind of elegant, and one looks kind of mischievous. Here's what their graph looked like at the start. So we have the Pleiades here and the Hyades by Hertzsprung, and then we have Russell with this one. Now, these stars are grouped in lines because he's using the OBAGFK KM classification, and they tend to, you know, you'll have a G5 star go down here, and this looks like a G9 star, so they tend to be in groups like that. Hertzsprung didn't use that. He used a different measurement based on the appearances in a spectrum. But you'll notice that his two diagrams of the Pleiades and Hyades both come out with a similar shape, which is a demonstration that what they're seeing in this graph, whatever it was, they didn't know, was a kind of universal categorization. It wasn't one that was unique to the cluster. And when Russell put his together, you also got the same pattern. It's tilted and spread out a little more, but you still got this group in here that all seem to line up, and then you've got this stuff off to one side. And so the question became developing the technology over the years to better refine the absolute magnitudes. You have to have the distance to the star to get that, to better refine spectral classification, which they did with the B minus B category, which is not discontinuous like this one, but allows you to have continuous placement. And so, when you put it together, you end up with, you'll find many, many diagrams of the HR graph. You end up with a pattern like this. In this graph of stars, there's something like 10,000 of them in this graph. Goes to much fainter magnitudes here. You'll see that we've got them in terms of the luminosity of the sun down to a 10,000th of the sun's luminosity down here, and up to 10,000 10,000 times or even 100,000 times. But you've still got your absolute magnitude on these sides because they're exactly equivalent to each other. They can be the other quite easily. Similarly, we have the B minus B magnitudes here, the color index, but up here we have the stellar classification according to the OBAFG scale. So, interchangeably, you'll find these things with different scales or different elements being plotted on each side. But you could easily go into a big group of stars with the color color index, as this is called, on it and plot them in a graph the same way I did with the subset from the observer's handbook. These different classes here, and they're given names, are related to the energy-producing mechanisms inside the core of the star. And in particular, this line, which is called the main sequence, the name here. The main sequence is where stars are burning hydrogen into helium. In other words, where most stars are getting their energy. Up in here, the stars are burning other elements to make even heavier ones, mostly burning helium up in here to turn it into carbon and oxygen. And down in here, we have a category of pretty faint stars, all the way from 1/100th of a magnitude of the sun down to 10,000th, which are called white dwarfs. And these are giants and bright giants and supergiants and so on. Not too much organization in this region, there's just scattered stars. So the question becomes, what is causing these types of patterns? Well, we want to go and look at how stars form, because this is as good a place as any to begin. And we're going to end where stars die, so we'll start with first. When a cloud starts to collapse into a star, it's perhaps 100 times the size of our solar system. And that size of a gas cloud may collapse into one star, it may collapse into several stars. And that's by no means a typical size. You get the Orion Nebula, for instance, which is tens of thousands of times our solar system, millions of times our solar system, which is collapsing probably into millions of stars eventually. Well, by the time it gets down to about the size of our solar system, it's what we would call a protostar, and it's not a star yet. It's still a collection of gas, but it has an internal temperature of perhaps 10,000 K. That heat inside this thing slows the collapse, the gravity that's pulling this cloud together, and it begins to collapse much more slowly. And it's releasing an awful lot of energy because it's a very big area. You know, we're still talking at least the size of the solar system emitting all of this energy. So the energy is not coming out at a very high temperature, at least through the whole of the gas cloud, but a combination of its temperature plus its size is going to make it pretty bright. This thing will continue to collapse. There's various mechanisms that come into play. It forms an equatorial disk. Things like this, it starts to collapse down, gets more and more condensed, starts to form a dense core. It starts to get a disk forming, and eventually it settles into a star with a dusty disk around it, which will probably later form into planets and eventually end up in this shape. And we're starting to see a lot of photographs of that with some of the great big telescopes that are coming online or have been online for a number of years. The 8-meter stuff, the radio telescopes like ALMA and things like that are beginning to give us actual pictures of that. Once we get to about 1 million degrees, 10 to the 6 Kelvin, the star, well, what will become the star, the protostar, usually pretty variable. It's starting to blow off a lot of the dust and gas. There's dust and gas still falling into it. It forms jets to blast some of this stuff off to the side. They become what's called T Tauri stars, which is just named after one of the early stars in the constellation Taurus, where they worked out this process. And in our diagram here that we were looking at, The T-Tauri stage would be probably somewhere in here where you would see jets glowing, or could see jets glowing material. The upshot of it is quite a bit of the material that was forming this star is blown away. But eventually it contracts, getting more and more star-like until it hits about 10 million degrees Kelvin, and that's when it can hotten up in the core to start fusing hydrogen and making helium out of it. And the energy that comes out of that reaction is essentially what powers all of the stars that are on the main sequence, conversion of hydrogen to helium. You still keep on getting contraction in the star until eventually the pressure of in the internal part of the star caused by the energy generation balances the force of gravity, and then you go into a very, very stable existence such as our sun has right now without a lot of variability. Now imagine what this might look like in the HR diagram. You start with a very large body that isn't particularly warm. So it's going to be red, because red is on the cool side of the HR diagram. And so there are two elements that come into play here: how bright or how hot something is and how big it is. So you can have something that's pretty cool but very large and can have a lot of brightness. But in any event, these clouds, as they're collapsing down onto the main sequence, are going from the red cool side over here, but still pretty bright. We're looking at, here's one, the track that our sun would follow, and you see that it's almost 100 times brighter than its current brightness. And that's not so much because of its temperature, but because of its size. As it gets smaller and smaller, the temperature isn't changing too much. It is gradually increasing, but the star is getting smaller, so it begins to look dimmer and dimmer till it gets down into here. This portion of the collapse is called the Hayashi track, and where it changes to becoming more horizontal, it becomes the Henry track. And these are just in recognition of the modelers who modeled the processes that were happening in the star, and were able to tease out what was happening. You can't see a star doing this, but you can calculate what it should do, and then you go look for a star. Well, I got one that's in this stage, and one that's in this stage, and eventually you put them together well enough. So at this stage, as it comes onto the main sequence, you'll see that very, very heavy stars don't change very much. They more or less maintain the same luminosity until they get right onto the main sequence. The birth line here is where some hydrogen to helium conversion starts up in the collapsing star. Now these can take a long time. They're not nowhere near as long as the time on the main sequence, but these can take a long time. So we see for small stars 30 million years to collapse from the gas cloud down to the main sequence, 100 million years for very, very faint stars, 0.16, 160,000 years for a very bright star. So bright stars evolve very quickly onto the main sequence. Here are some photographs of a cloud of dust and gas that is collapsing. There are stars in here. Some of those stars are setting out jet material, and you see them as little bright, almost comet-like things called perigperal objects. And I think we had a talk about those some months back. But these HH objects are quite photographable, and they're quite included in here. Although at this scale of picture, you probably want a Hubble telescope to zoom in on them. So what we have now is a collection of objects along the main sequence. And they range from cool small stars down in here to blue, hot, and very large stars up in here. They're all burning hydrogen into helium. The helium is accumulating in the core of the star. So the hydrogen is actually being diluted over a period of time by this ash of helium. Over here we see the lifetime of stars on the main sequence. So we're looking at 100 billion year stars for stars that are fainter than our sun down here. Here's our sun. Our own sun lifetime on the main sequence, about 10 billion years. We're halfway through it right now. Stars down in here are going to be going on for 2, 3, 500 billion years. You really want to have a civilization that lasts for a long time, you want to find yourself a cool red star. And some of them, like the one Jennifer talked about, we're actually finding cool stars around these very, very, or cool planets around these cool red stars. Once you get much brighter than the sun, here we are down to 1 billion years, 100 million years, it starts to chop off. Of course, the main thing is we sort of like teenage stars, they burn through their energy very, very quickly. Whereas this is where I am down in here right now. I don't have a lot of energy to spare. I'm burning through. What happens when they're on the main sequence? Well, the core of the star is filling up with helium. When we started our existence on the zero-age main sequence, which is right here, we were 74% nitrogen and 25% helium. Now we're 35% hydrogen and 62% helium. We burned up a lot of hydrogen in the core of our sun. But it's still putting out heat, and in fact, modeling shows that as these stars age from the main sequence, and here's one of the mass of our sun, they actually brighten somewhat. You know, it's not very much brightening, except that that distance there probably represents perhaps a doubling of the brightness of our sun, which is a little bit of a cause for concern because it's enough to do some serious global warming here. The sun were to double its brightness. Well, we're halfway along. The sun has actually brightened over the years, and at least our modeling tells us that. Other stars also brighten as they move away from or up to the upper right. So when you're moving up this way, we're going straight up. Most of our changes in brightness. Other stars are actually getting a little cooler, but they're getting more luminous, and that tells you that they're expanding a little bit. They're brighter, not because they're hotter, but because they're bigger. So their atmospheres are spreading out a little bit. Whether or not that's a good thing, we get more luminous, but our temperature doesn't change, which means our sun is going to be swelling up somewhat over the course of its evolution. This is quite a long time to do this. For the heavy stars, this process goes by pretty quickly. And eventually, pretty much all of the stars gradually move to more luminous and slightly cooler existence as time goes on. And they have a certain lifetime on that main sequence as they go from the zero-age main sequence to the terminal stage of the main sequence. And you can see stars that are 25 times the mass of our sun have a 6.5 million years, whereas stars that are our sun, 9.4 billion and less than our, just a small decrease of 20% in the mass of our sun has a huge impact on the length of time that it would be on the main sequence. So we need to find a nearby, maybe a G0 star, something like that, or a K9 star. It's the dog star, serious, little series, K9 star. Anyway, besides, Sirius is the wrong color. When you're on the main sequence, you're burning hydrogen into helium in the core. Now these three types, there's an O star, G star, and an M star. You have to realize I've drawn them all the same size here, but this star is 60 times as big as this one, and 600 times bigger than this. So this one would be a little tiny star, and this one would be a great big star. But by relative proportion, there's a much bigger core in the M star that's burning hydrogen into helium, and then it has a convective zone around it. And those convective zones are where material is moving upward, bubbling up, just like water bubbles up in a boiling pot. And they sort of change their internal structure. So our star has a convective zone on the outside and a radiative zone on the inside, but the heavier stars are reversed. And these guys are taking all the heat from internally out to the surface just through mass movements of like pudding boiling and turning over. The radiative zones are important in our star here because it takes a long time for the energy released in here to make it through these radiative zones. You know, these gamma rays are moving half the width of an atom before they're captured by an atom and then have to be re-emitted. So they're making tiny little jumps to get out. But once they get out to where the convective part is, the energy moves out to the surface where it can be radiated away quite a bit more quickly. So when a star gets to the terminal part of the main sequence here, something odd happens. We've got this helium lac of ash left behind, and so the fusion, eventually there's so much ash, just like in a coal furnace, it's not burning as hot as it used to. The hydrogen atoms are, actually protons can't find each other quite so easily because there's all this helium in the way, so the fusion rate goes on. All of a sudden there's not enough pressure in the center of our sun to withstand the gravitational pressure from everything around it. And so the core contracts a little bit, that raises the temperature, burns a little more furiously, and so everybody takes this little jump upward. Well, that little tiny jump, if there's anything left on the Earth by then, it gets fried at that point. So even though it's a tiny little jump, they all make it except for stars that are sort of solar mass and lighter. They just keep on going up until they run out of hydrogen in their core, which is where they are on these upper dots. At that point, they have to change over whether they're burning, and there's about two, I'm just estimating in the middle here. You're probably in that sequence that we have here, the sun's brightness does jump upwards because it'll be right here and then takes a little bit up like that. So now the stars that were on the main sequence, as soon as they've run out of this helium in their core, it consists now of a mass of helium in the center with some hydrogen mixed in, and then everything else out beyond that is still hydrogen. That doesn't burn. So you basically have a shell of hydrogen around the helium core. So what we have to do is these stars move off, they're running out of energy. So they have to go to a cooler temperature, a redder temperature. But they also swell up. So even though they're cooler, they become brighter because their atmospheres swell up. So let's have a look at that. Initially, they're not giants or supergiants. They have to pass through this region in here where they are actually subgiants. And a subgiant star, once this helium or its core collapses because it's no longer generating energy in here, you end up with, very quickly, a star with helium in the middle and an area of hydrogen burning around it. And the reason that hydrogen can burn is because the core has collapsed a little bit. And of course, when it does that, it heats up. So now it's getting a high enough temperature that it can burn this somewhat less dense hydrogen on the outside. And so it goes on burning hydrogen in here and adding more helium into the core over the next stage in its life cycle. And what happens is that this hotter temperature in the center causes the atmosphere of the star to swell outward until it becomes considerably bigger than it was. And even though it's now at a cooler temperature, because as the atmosphere expands outward, it cools, but now it's a much bigger object. So we get something like Betelgeuse, for instance, which is a star which has got a greatly extended atmosphere. It would extend all the way up to Jupiter if it were in the place of our own sun. But it's a very cool star. So in this initial stages of leaving the main sequence, it travels horizontally along these lines, getting cooler and cooler, but keeping the same luminosity. The expansion outwards is compensating for the cooler temperatures generally, and so it maintains a similar luminosity. When they get to this stage, they start now to increase the luminosity. And that stage occurs pretty much at the same point as all the stars, at about 5,000 degrees in the external surface temperature. And so they all start climbing upward, sometimes with various zigzags. What's happening is you're getting a hotter core as this helium is accumulating and the core is contracting more and more, getting hotter and hotter. The area that's burning hydrogen gets to be bigger and bigger because this ball in the middle is expanding outward. So you're getting a greater surface area of hydrogen burning. And so we begin to climb up this stage. So we go from the sort of proto-red giant into true red giant stage when it starts to make this upward climb. So this process of switching fuel sources inside the star has a major impact in its evolution, because after it moves off the main sequence, the length of time that it will be able to produce energy decreases considerably. If you have a lightweight star, you're going to eventually put so much helium in it that the helium contracting by gravity is going to reach what's called a degenerate state, which means it's packed so closely that it cannot any longer collapse. It's not being supported by temperature anymore, but by quantum effects. It's actually going, in some respects, like a great big atom all by itself. The core shrinks and heats up. The heat that's there increases the hydrogen burning through a different CNO cycle, for those of you who know something in a little more detail about this. All of a sudden the hydrogen shell starts to burn more fiercely, and that's when it makes that climb upward to become a true red giant. So the red giant is essentially a star that's burning using this particular cycle. It involves carbon, nitrogen, and oxygen, or primarily carbon and oxygen, to act as a catalyst to help the conversion of hydrogen into helium. That lasts about 2 billion years for our sun, but an awful lot shorter for other suns. So here we have a picture of Betelgeuse when it's in the red giant stage, and this is an actual picture of the surface of Betelgeuse. It's not a picture of a bright point of light that's spread out in the photograph. It's so big we're actually able to see its surface. But what's happening is we've gone off the main sequence, we continue to swell up as these internal processes change in the center of the star. Still burning hydrogen into helium. For really big stars, they never become degenerate at this stage. They just get a bigger and bigger atmosphere. The core continues to heat. At some point, the atmosphere stops being transparent to the radiation coming up from below, or as transparent. The star then doesn't cool anymore because the radiation is being trapped inside the star, and the rate of fusion increases, and that's how the heavy stars make it into the red giant phase. So one kind of star has got this degenerate core, but it's still got this hot burning around it. The other one never does it. The hot burning is internal. These are just sort of little nuances on what happens, the difference between big and little stars. So when they first start into this red giant stage, as we pointed out, they have temperatures around 5,000. The core continues to increase in helium. Fusion in the shell increases because this core is collapsing and becoming more and more hot, higher temperature. And you're beginning to create elements like carbon and nitrogen and oxygen inside the star. Not very much, but the CNO that's there starts to, you get a big convective outwards, and so it starts to dredge up material from inside the star. This is important because when you look at these stars, you start to see increased amounts of carbon and oxygen in particular on their surfaces, which tells you that they're in the situation of shell burning here. With the degenerate core, eventually the helium becomes the amount becomes so large, and it becomes capable of actually igniting helium so that it can burn to form heavier elements. So it turns on a new fuel supply in the center in the later stars. And when this happens, this helium flash is almost instantaneous, and the star suddenly stops being a nice, cool red giant and becomes a much, much hotter star, and it makes a very sharp turn off of the evolutionary sequence. Let's see if I can get back to here. And right here is where the helium flash occurs, only in the lighter stars, and the star immediately makes a shift to higher temperatures and moves back actually toward the main sequence. It has no relationship to what's happening on the main sequence because now it's burning helium. And so what you have is a shell of hydrogen around the outside that's burning. You have a core of helium that's burning into carbon and oxygen and some of the other elements. And you have a core of helium surrounding that which isn't burning. And you have outer atmosphere of hydrogen, which at some point may burn. And you can imagine that this hydrogen burning increases quite a bit when this helium burning turns on, because now you have a double fuel source inside this star. And so what happens is if you look at the main sequence and you look at, say, a cluster of stars where a lot of them have turned off the main sequence, you can see them up in here where the initial stage is now into the red giant stage. So stars don't, it's not a movement so much along the HR diagram as an evolution into the different stages. Helium flash is explosive. Our sun will become 40 times hotter when it gets to the helium flash stage. It moves down toward the main sequence more or less in a horizontal fashion, and so it becomes part of what's called the horizontal branch, which is this branch here. It's a relatively long life stage, although not the 10 billion years that we've had on the main sequence. But it's been referred to a couple of times as the helium main sequence. So here we are with the helium flash here. The increase in temperature gives considerable increase in the energy that comes out. So we have, when you look at I'll have to show you this later, we have what's called an asymptotic giant branch, which is also the early stages of the horizontal branch, lots of different names. Well, with the low mass stars, we've now, when we're burning helium in a core, or in the core and hydrogen around it, that's essentially the end of the fusion mechanism in the star. It's not heavier enough to go anywhere else. So the atmospheres of these stars are spread out a bit. They're very easy to shed, and they do shed them into planetary nebula, which both Stan and Gail referred to. At that point, there's no more fusion left, so what we have is this star that's blown off its outer atmosphere to form a planetary nebula. It reveals the core of the star, which is mostly helium and carbon and oxygen on the surface of it, and some little bits of hydrogen, and it becomes a white dwarf, and it has no other fate other than to cool off slowly. It's moved along the horizontal branch, drops down into and it cools very, very slowly into a red star. Here's a picture of Sirius. Sirius has a companion that's a white dwarf. You can actually see that visually if you get say a 10-inch telescope and take some care to look very, very close on a very dark and stable night alongside Sirius. Here's what the size of a white dwarf star would be like compared to the size of the Earth. So all you're left with is what is initially a very hot core coming down this way that just cools off over billions and billions of years until it becomes what's called a black dwarf. The hotter stars, they follow a somewhat different evolution. They've moved through their sequence much more quickly. Here is M5, which Dan talked about. M5 is a globular cluster, and here's the main sequence on it. Most of the stars have moved off the main sequence here, and they become red giants up through this stage. In here, there's some of the colors, RGB
is the red giant branch up in here. Main sequence is in here. Here's our horizontal branch here, and this is the asymptotic branch. Asymptotic meaning it converges with these two lines. So you can get these two stages. But remember, these are stars they're not moving in here. They're red giant stars that have moved in here, and finally when they use up most of their core hydrogen burning helium, they move on to this asymptotic giant branch and eventually move down in here. Notice this little gap in here. So they spend a lot of their time in there doing helium burning. Eventually that has to end. So the high mass stars, because they've got so much mass, the ash that burns up from helium, carbon, can then be ignited. Carbon and oxygen can go on to fusion, and silicon fusion, neon fusion, magnesium fusion, until they finally get up to iron fusion. And the problem is, all of these processes give off energy, although very little of it. When you start to burn iron, it takes energy. It immediately robs the star of its internal energy source. The minute it accumulates iron in the core, and the star immediately collapses when that happens. It's like cooling the center of it to no longer support all of the extended atmosphere around it. It collapses inward, and when doing so, creates a supernova. So what they're doing is they're in the red giant and the supergiant stages in here, burning hydrogen, carbon, and oxygen, and then finally when they collapse, the process results in this supernova explosion, which blows out into the galaxy all of those elements that have been created in the center. And at that point it disappears off the HR diagram because we don't know quite what to do with it. Depending on the mass of that star, it can form a neutron star or a black hole. But certainly once it's got an iron core, it's doomed to a rather spectacular failure. And that would be the sort of heavy stars, sort of more than about 8 times the mass of the sun, end up as supernovas, and anything less than that ends up as fading away as a white dwarf. And there are ways to make a supernova out of a white dwarf, and that's a different process. Normally, they're on the main sequence of mass no more than 8 times the sun, but that gets reduced to no more than 1.4 times the mass of the sun, usually by expelling gas and atmosphere in this planetary nebula. So it loses most of its mass. If it comes in higher than 1.4 times the mass of our sun, by the time it gets to the white dwarf stage, it'll actually collapse into a neutron star. So it's kind of a pretty sharp separation between big and heavy stars in this case. It's a carbon and oxygen, so if you look at the spectrum of a white dwarf star, you see lots of carbon and oxygen in it. It'll keep on cooling. Initially it might have temperature, because it's the original core of a star, could have a 35,000 degree temperature. But over a few billion years it'll drop down to 400. That's when the star gets to be a little bit like a giant crystal, and then it just continues downward along to the right of the HR diagram, getting redder and redder, fainter and fainter, until it turns into a black dwarf. Of course, we're nowhere near enough time in the age of the universe so far for that to happen to anybody. In fact, any star less mass than about 9/10 of our sun has not had enough time to turn into a red flame in the age of the universe. We sort of reiterate everything following the track of our sun. So we're now on the main sequence. We're burning hydrogen for 4.5 billion years. At about the 10 or 11 billion year mark, we're going to be moving, swelling up. We're going to be getting cooler. We're going to start burning hydrogen in a shell around here, become a red giant at this stage. The helium flash will ignite here, drive us back
to a higher temperature here, blowing off some of our atmosphere, we become a yellow giant at this side, so this would be a subgiant or perhaps a small red giant. But because we're losing atmosphere in here, we're probably not going to be big enough to be that color. But we're a hotter color, we're gone from red to yellow. Eventually, we end up burning helium in the core. We end up getting an atmosphere that expands so that we look cooler, even though our temperature is falling down as low as 3,000 degrees on the surface. We throw out the planetary nebula in here, and we're left as a white dwarf, just scoop across this area and drop down into the white dwarf stage. And for other stars, the heavy stars follow that very quickly. We remember in the diagram they have a little bit of zigzagging back and forth in here. There's a region in the HR diagram called the instability strip, and stars that are passing through that region tend to be variable stars. And in fact, a couple of important classes of variable stars, and particularly the Cepheid variables, are our Lyra stars, and these type 2 Cepheids here are sometimes called WB Virginian stars, W Virginian stars. So it's an interesting process, and it's caused by the formation of helium-2 in the star. Helium-3 is opaque to light, so when up in the stars it expands for helium-3 to form, it traps radiation. Helium-2 traps radiation, so the star swells up. As it does, it cools. The helium-2 then becomes helium-3, and it collapses back. So it's just the capacity changing because of different ions of helium that causes the star to swell and shrink. And we can use that to tell us an awful lot about distances of stars, because Cepheid variables, for instance, you can tell how bright their intrinsic brightness is by how rapid their period is. It goes from brighter to fainter values. A nice, well-behaved variable star that when you measure the light curve on it, you could say, well, this star is a -10 absolute magnitude, and if I detect it in another galaxy, which we can because they're bright stars, then you can say how far away that galaxy is. If you take a cluster, a globular cluster or an open cluster, plot all the stars, you get that pattern that I showed you, but you can tell how old these clusters are by how many stars turned off the main sequence. So you can get a very old cluster, such as M67 here, where it's turned off for stars that are only, say, double the mass of the sun. But if you go up here to the ancient Chi Perseus, the double cluster in Cassiopeia, or Perseus rather, you'll find that the stars are very, very young. The age of the cluster is very young because only the very heaviest stars that evolved the most rapidly have turned off the main sequence. A very accurate way of determining the age of a cluster. Here's some examples. And you see we have 10 billion year old clusters here and here, 13, almost 14 billion year old clusters here and here. And you can see some subtle differences, even though these are not all on the same scale. But for instance, the younger ones have this little cluster here called a red clump, and this one where it's missing in these ones here. Some hint of it in that one. So that may be a structural change. The red clump is caused by the fact that a star that comes off of the main sequence is a subgiant and then becomes a giant, gets up into this stage and actually zigzags back and forth in this area as various energy processes turn on. And so they tend to come in this area, coming this way and this way. They clump up before then they go back to become their planetary nebula and white dwarf. This I brought in because it's probably the most accurate cluster HR diagram of all. Very, very careful study of this particular cluster here using the Hubble telescope, making sure that all of the stars that were in the foreground or background were removed. And so we're down to 30th magnitude here, pretty much, for the very faintest stars that can go onto the main sequence. Much below that, stars will just remain as great big Jupiters, they won't, or bodies will remain as great as Jupiters, not stars. Very, very nicely defined main sequence, the turnoff point right in here, and then is starting to think about what's happening down there in that very faint white dwarf state. And you can see we've got a white dwarf in here, which is almost at 30th magnitude. Interestingly, that about 98% of the stars in that cluster will end up with white dwarfs, which is where we'll be meeting them. So, in summary, the HR diagram, while it's simple in concept, is an incredibly powerful diagram for finding your way around the collection of stars that we have in the universe. I'm showing this graph just to show you that some people plot them backwards. So that now we've got the low temperatures here and the high ones here. So you'll get HR diagrams in a number of different shapes, but you'll almost always be able to recognize the main sequence, the giants and the supergiants, and the scattering of stars in between them that are on their way to other fates. I suppose it's only appropriate that I leave you with a picture of a black dwarf, even though we don't have one in actual existence. So the background here is a picture of a black dwarf. Thank you very much. I'd say ask me some questions, but it's pizza time. So how about if you ask me questions with pizza? I won't say I can guarantee your answers because the theoretical modeler would probably be much more capable of explaining these details. What I did find interesting in this whole process is that the actual details have not changed very much since I studied this at university back in 1972. So I think we've got it down pretty close to what that is.